today we will start with the big data. So, the idea here is we will capture a bunch of political news articles in a streaming manner, in a continuous manner. So, now we need to do classification or prediction. So, but keep in mind that those political those articles we are gathering, it will come continuous basis. So, as a stream basis. So, we will go to the Guardian website every hours or every 30 minutes and capture the or download the news articles and then try to classify it on the fly. So, that is our goal today. So, in order to do that, we need to know a couple of things. The first thing is how we can process the stream data, and second, this data will grow over time. So, we need to exploit some big data technology. So, more specifically, we will talk about Spark today and Spark streaming, and then we will talk about also how you can capture this news articles from the Guardian website in a seamless manner using some sort of queuing system called Kafka in this case. We will talk about that more details. And then we will go through the details about the hands-on and so on at the end of the day. So, first I will start with the what is big data, and then I will introduce you Spark. Okay, so motivation behind the big data is that a single machine will have its own memory and the disk, and when the data are continuously coming and growing over time, you may not be able to process that data using a single machine. So, we need to come up with a distributed computing or parallel computing. This is not a new concept, it has been there for a while. But the new thing about big data or a big data area, the idea here is we are going to use the commodity hardware. So, the machines we will a bunch of machines will group together and form a clusters, and those machines are very cheap. So, if it is cheap, then this machines will form number of machines will form a clusters that will give you the distributed framework or parallel processing. But what will be the problem with this type of framework or number of machines which are commodity which are not that expensive, basically commodity hardware. Yeah, so it may fault, it may that means it may fail at any time. So, if it fails, that means you have to come up with a fault tolerance or recovery mechanism. Let us say you have 3 machines and you form a clusters, machine 1, machine 2, machine 3, and you want to run certain task, and you divided and you want to process read data from a big file. So, you split that file into 3 blocks, and each block will be processed by one machine. Recall that I have 3 machines clusters. And now, if one of the machine is failing, then what can I do? Then I have to wait unless the machine is available or up again. So, that will be an issue. So, how we can tackle that issue? So, for that, the idea here is we will do the replication. So, the original raw data, the big file will be split into 3 blocks. That file will be replicated, or that 3 blocks will be replicated into multiple machines. So, if the replication factor is 3, so instead of keeping 3 copies, block 1, block 2, block 3 in 3 machines, we will keep total 9 copies, and each block will have 3 copies in the system. So, one machine may have block 1, block 3, another machine may have block 2 and block 3, something like this. So, that way we will take care of the fault tolerance. That means, if a certain operation is going on a particular block or file partition, if the machine is failing, then it will be run in a different machine where the block or partition will be local. That is the main idea for the Hadoop and MapReduce. Okay, so here what I try to say that traditional database management system can handle a large volume of structured data and so on, but they use the parallel computing like Oracle. When you buy Oracle product, you need to you may need to use expensive hardware to facilitate parallel processing and so on. But here, or expensive server you will use. Here what we are talking about in big data area, we are going to use the commodity hardwares. Those machines will form a clusters, and this where the machines may fail at any time. So we are going to use the cluster of machines, a number of machines, and those machines, any machines can fail. So that's the key point here, keep in mind. That's why big data technology is very popular, because it uses the cheap commodity hardware and so on. And now, before going to talk about more details about the Spark framework, I want to introduce you the big data. What is big data? Big data basically the data will grow over time, or it has a very large data set and so on. And there is no standard definition for big data, but what we say for big data, I will explain to you in a minute. There is no standard definition for big data, but we keep in mind that big data means where the data will have a bunch of V's. Those bunch of V's, I will explain that in a minute, but in a nutshell, you can think about if the data is very big, large volume, comes with a very high speed velocity, and then varieties, it will not come in a structured form. It can be unstructured, semi-structured, and then typical structured data. Then it may contain the erroneous data points or veracity is involved. So in that case, if the data fulfills some certain V's, then it will be known as a big data. So let me explain more details, but before that, who generate this big data? Nowadays, you know that all this online shopping, when you do, the backend server captures your information and so on. So that over time, that generates humongous amount of big data. Then in the social media like Facebook, Twitter, Instagram, in the past, like before the social media became popular, we used to read the newspaper articles, right? And bunch of newspaper articles, publisher publish the news articles, and we just consume it. So at that, previously the paradigm was we are the consumers, and the producers may be the newspaper articles, whoever wrote the articles and so on. But nowadays, the paradigm has been shifted. In the Facebook, many of us are posting the messages and brag about ourselves and so on. And at the same time, we are reading our friends' post and so on. So we are not only consuming the content, we are also producing the content. That's the key point here. So in Facebook, we are not only the consumer, we are also the producer. So that generates humongous amount of data and so on. Then what is the characteristics of big data? I said big data will have a large volume. It comes with a very large velocity, with a very high speed. Then it will not be only structured, it can be unstructured, semi-structured and so on. And if we can, when you want to deal with the big data, you want to make sure that will produce some values or give you some benefit in terms of financial benefit and so on. And the data we will gather from various sensors or environment that might produce erroneous data. So when you develop some algorithms with this data, you need to make sure that we need to take care of the veracity issue. So here the volume means before we used to deal with the terabytes of data, now we are dealing with the petabytes of data, and then over time the data is growing in exponential rate. So here Facebook every day generate more than 500 terabytes of data, and Boeing 737 will generate 240 terabytes of data when it flies from say Los Angeles to New York or vice versa. So then a sensor will also generate humongous amount of data, and then velocity So, keep in mind when you do the database, in the database we usually keep track of the transaction, right. So, if you want to withdraw some money from your account, then what will happen underneath? Underneath the database will first verify whether you have a whatever the money wants to withdraw, whether you have that amount or not. If you have that amount, then your corresponding record in the database will be updated. Let us say you have $100 and you want to withdraw $20. So, your record will be changed, amount will be changed in the record from 100 to $80. So, that is called you are doing. Sometimes you do the read operation, in this case it will be a write operation, basically you are updating the records. But here when you talk about the big data, I said the data coming with a we are dealing with a very large data set, but here one of the assumption most of the cases that data will not be updated. So, in a social media when you post your messages, what happens? Do you update? Probably not, you rarely update, but in a typical database world, you just you may delete the records if you do not like it. If there is a controversy, you may delete the records or delete your entry. But here in this big data area, the idea here is we assume that write once, read many times model. So, once the data is created, it will not be changed, but you can continuously add new records and so on. So, that is the paradigm we are going to talk about here. Another way you can think about, every time you create a new you want to update a record, you can keep the old record with the timestamp and the new record you will create with the new timestamp and so on. And then when you need to deliver the content, you may deliver the most recent content because you have the timestamp, right. So, okay, so what I am saying, let us say this is your account, social security number, and then you have amount $100, right. So, in this paradigm, we will keep this record and say the timestamp is this, I have this amount. And then you are changing for the same social security number, the record will be $80 now. So, we will put a new timestamp there. And now query comes, I want to know how much money I have. So, it may give you this result or it may give you this result. So, which one it will be delivered to you? So, this transaction happens let us say at 10 a.m. and this transaction happened at 11 a.m. on the same day. So, which one the system should return to you? The most recent one, right. So, based on the timestamp you can determine which one is the most recent one or the correct one. So, anyway, so so here I am saying the data will come, some cases data may come with a very high speed. Say for example, sensor generate massive log data in real time. So, that means the system needs to cope with this a large volume of data that will come continuously, and then when people play the online game, so you know that also generates humongous amount of data, and this data will come with a very high speed. So, you need to consume this data the way it will be generated at the same speed. And then I try to say data can be not only structured, that we always know very well that relational database like tables and so on, but data can be unstructured also like HTML page, XML, these are semi-structured data. Then data can be come from the sensors, this will be a streaming in nature. And so, furthermore social network will generate the social graph, this can be a that can be a graph data. And then data can be, we need to determine the trustworthiness of the data. So, data will come from the various sensors and from the environment, and there is a possibility that whatever the content or the data we will gather or we will collect, that may have some erroneous values. So, when you develop some algorithms from this data, we need to make sure that we should not assume that all the points or all the data are correct. And then when we want to handle this data, we want to waste our resources and so on. So, we need to make sure that that will add some values. Okay, so in big data, the idea here is we are going to deal with this heterogeneous collection of data, where we want to develop new algorithms that can handle this big or large volume of data in a scalable way. So, for that we need to develop some sort of distributed algorithms that can handle very large volumes of this data, that type of things we want to talk. Okay, now before going to talk about Spark, I just want to emphasize a little bit about Hadoop and MapReduce. Okay, say I just want to introduce you what is map and what is reduce. This comes from functional programming. I give you a list, say 10, 5, 7, 11. And I want to this list consists of a number of elements in this case, and I want to apply a function operations. In this case, the function will be square. It will produce, if I take each element, and what the map does, it takes a list as an input and it applies some function each individual element and produce a new list. So, when you apply map operation, it will take each element from the list and apply a function. In this case, the function is maybe just take the square of each element. So, it will produce a new list with 100. What will be the second one? 25, 49, 121. And in this case, the reduce case, let us say it will take a list as an input and we want to sum it up. So, we want to take this list as an input, 10, 5, 7, 11 as an input for the reducer, and then reduce will start to accumulate the results. So, it will take the first element, and accumulator will have initial value 0. So, after accumulation of the first element, it will be 10, and then it will take the second element 15 in the accumulator, then it will take this third element 22, then plus 11. So, it will be 33, and it will emit that result. So, that we do in the map reduce case. Now, if I give you a very large list, so this list contains a bunch of numbers, num1, num2, num3, blah, blah, blah. But before going to talk about that, now let us say how the parallel processing can help. So, let us think about, we have total 4 elements here, right?
Yeah. Don't you usually reduce the map, the result of the map?
Yeah.
Okay.
Yeah, result of map. Yeah, I just give you an example. Yeah, yeah, I agree with you. Usually, a map or output, we will reduce it from there. Okay, so now let us say I give you 10, 5, 7, 11. So, these are the 4 elements in the list. If I want to process it using a sequential, using a one computer or one machine. So, this will process first, it will produce 100, then it will process next, it will produce 25, 49, 121. So, if I do serially, how long it will take? Each element takes one time unit. So, it will take 4 time unit. Do you agree with that? So, whatever that time unit I am defining, and on the other hand, let us say I have 4 machines. So, each machine will take one element at a time. So, then 10 will be the input for this machine, 5 will be the input for this machine, 7 will be the input for this machine, and 11 will be the input for this machine. So, and those machines, machine 1, machine 2, machine 3, machine 4 will be run in parallel. If we can run in parallel, then what will happen? So, let us say all these machines are smart, they do not take that much time. So, 1 time unit each of them will take. So, if there is no delay or no failure of any of this machine, then what we can say? We can say that this list will be produced 25, 49, 121 will be produced in 1 time unit. So, that way you can speed up the processing. That in the MapReduce case, what we do? We divide a very long list like this into a sub list, and each sub list will be processed by one machine or a sub, just an example. And then those sub lists can be each of the sub lists, let us say, will be fed into a machine, and these machines will be run in parallel. That way you can speed up. So, now instead, let us say, instead of using 4 machines, if I use 2 machines, then what will happen? So, before, if I do it in a sequential manner, it takes 4 time unit, right? But if I have now 2 machines I have available, so 10, 5 will go to one machine, and then 7 and 11 number will go to the another machine. So, how long it takes to produce the mapper output? This will take 2 time unit, this will take 2 time unit, this will work in parallel, right? So, it will be 2 time unit. So, that way we do the speeding. Now, let us talk about a simple example. So, you have already Hadoop MapReduce background, you have or you know Hadoop MapReduce? Okay. So, let us say that is why I am trying to cover a little bit, and then I will move towards my main point. So, we have a bunch of numbers, say number 1, number 2, number 3. So, this is a millions of numbers I have, and my ultimate goal is to do the summation. So, how you can do it? So, you can run it take one input at a time, and you will do say let us say this is a list for each E in the list, and sum equal to 0, right, at the beginning. So, sequentially you can do something like this for each, and then so, if I will implement this in a, I will say sum so, this is a key value pair, this is not important. So, I will just emit the sum, right. So, that will be my sum, I just print the sum, right. That is a simple logic you can implement, right. Now, if I want to do it in a parallel way or using Hadoop MapReduce. So, what I will do, this list will be divided into a sub list. In a Hadoop sense, they call it block. So, block 1, block 2, let us say this list is divided into 3 blocks, block 1, block 2, block 3. Now, block 1 will be, let's say we have a replication factor 2. So, each block will have a 2 copies in the system. Replication factor is 2. So, total 3 blocks, that means in the system we will have 6 blocks. So, block 1 will be stored in machine 1, and then block 3 also stored in machine 1, and then block 2 is stored in, let's say, machine 3, and block 3 is stored in machine 2. And then let's say block 2 we keep it in machine machine 4, and block 3 we keep it, another copy we keep it machine 5. Okay. So, now what we will do? So, mapper program will be run at this node, at this node, at this node, and each of this mapper program will take block 1, block 2, block 3. So, here M2 machine will take the input from block 3 and produce local sum. So, this code will be run, but it will produce not a global sum, because here block 1 consists of not the full list, it consists of a sub list. Do you agree with that? So, it may contains, let us say, couple of thousands of numbers, and it may contain another thousands of numbers. So, each of them will produce, if I run this code there, each of them will produce local sum. Then all of this local sum will be sent to the one machine, which will serve as a reducer. There we will aggregate this local sum and produce the global sum. So, where the power comes, why this? If I run this code, probably it will take, in a single machine it will take a long time, but when you divide the when you run the map reduce type of implementation, because it will be mapper will be run in parallel, in that case we can speed up or we can scale up. That is a very rough way you can say how the map reduce works. So, I just give you ABC of Hadoop MapReduce. Do you have any question for this? Okay. So, the problem with the Hadoop MapReduce was very popular, it works very well, but when you have a iterative job, you will see the machine learning algorithm we are talking about, like clustering, where you run many iterations, or even the decision tree, you may do a lot of loop or iterations, or any other classifier, you may need to go through a lot of iterations and so on. So, in that case what will happen? So, if you have a iteration or loop in Hadoop MapReduce, you will see the data sharing is done through the disk. So, this is one of the problem. Every time if the output mapper produce some output, do you know where this output will be stored? Mapper output will be stored on the HDFS file system. And you keep in mind that when you store it in Hadoop file system, they keep multiple copies and so on. So, next time when you need to read, it will read from the disk. So, in Hadoop MapReduce, the data sharing will be done through the disk. And now, if you have a loop, let us say you run a certain job, and then that output will be the input for the second MapReduce job, and the second MapReduce job output will be the input for the third MapReduce job, and so on. So, from one step to the another step, this data sharing in Hadoop MapReduce case will be carried out through the disk. And when you go through the disk, what will be the problem? Usually disk read write is very expensive as compared to memory read write operation. So, that is why Hadoop MapReduce is not good for iterative job and so on. So, in order to overcome the deficiency of Hadoop MapReduce, Spark was developed. Spark was developed at UC Berkeley at the beginning, and now it is a part of Databricks. and the most of the code was written in Scala, but it supports Python and okay, so written in Scala, but API is not limited to it. It supports Java and Python also, and even you can do SQL type of query language. It supports you Spark SQL. Even you can write your code in R. You know the MATLAB type of programming language called R. You can write your code in that language also, and it supports data frame concepts, which is a part of system R. So it provides programming abstraction and parallel runtime to hide the complexity of fault tolerance and slow machines. So we'll talk about that in a minute. So the main powerful feature of this Spark comes from the RDD, resilient distributed data set. Is a data container, and so let me explain the RDD in a minute. When you create so you have a so when you let's say you, and this RDD supports the fault tolerance. So I will explain the RDD a little bit details in a minute. So before that, let me motivate you why you need to use the RDD type of data structure. So you have a, so this is the Hadoop framework. So you have a input data that is part of the HDFS file system. Basically, we will have a data will be split into a number of blocks, and each block will be stored into a in the file system with the multiple copies. And we read the data from this block, and then we do some iteration or some Hadoop MapReduce job operation and so on, and then this will produce some output, and this will be written on the disk again, and then second iteration we will read the content from the disk. Whatever the first iteration produced, we will read it from the disk, and then second iteration will produce some output that will be written on the disk, and third iteration will read as second iteration's output from the disk. So again, you can see from one iteration to another iteration in Hadoop MapReduce, data sharing will be carried out through the disk. And I try to tell you that when you do the disk I/O operation is very expensive, and so it is slow due to the disk I/O, but due to we use the disk, so it will give you better fault tolerance because you will store it into the HDFS file. That means you will keep multiple copies in the system. If one machine is not available, then it will be the same copy may be available in a different machine and so on. Now, instead of data sharing through the disk, in Spark, data sharing will be carried out through the main memory. So the idea here is iteration 1 will produce some output. So iteration 1 will take the input from the HDFS file. That is not an issue here. But when it produces the output, this time it will not produce the output like what Hadoop MapReduce we used to do. We wrote it on the disk. This time it will be written on the each machine's main memory or RAM. Now, iteration 2 will needs to read the iterations 1's output. So it will be read from the main memory of machines or RAM instead of disk. So that way we do the splitting. But how do you now the problem is, if this machine is failing, that means that machine's RAM is not available. So that means let us say iteration 1 produce some result into the machines 1 RAM, machines 2 RAM, machines 3 RAM, and iteration 2 starts to read the machines 1 RAM, machines 2's RAM content, machines 3's RAM content. Now, all on a sudden machine 1 is failing. That means what? Machine 1's RAM is not available, right? So how do you facilitate fault tolerance? That we need to deal with that here. So we will design a distributed memory abstraction that will be efficient because data sharing will be done through the main memory, but all at the same time it will be fault tolerant. That we will explain in a minute how we do the fault tolerant. So, what is RDD? So, this abstraction will be carried out through the resilient distributed data set, or RDD, is a restricted form of distributed shared memory. It is immutable. Once you create, you cannot change it. It has been basically this immutable RDD, you can think about it consists of a number of records, and these records will be distributed across multiple partitions. In other words, each partition will contain a number of records. And it can be built through the coarse grained deterministic transformation, like so let us say this is my HDFS file. So, it has 3 blocks and the replication factor is 3. So, therefore, in the system there will be 9 blocks, right. Now, when I want to create a RDD, let us say I want to do a filter operation. So, what I will do, each of this record contains, let us say, a field or column called zip code, and zip code for 75080, I think for UT Dallas zip code. So, I want to keep only the records that satisfy this condition. So, what I will do, I will run 3 mappers operations, and each of the mapper will process this B1, B2 partitions and go through each individual record and check whether the zip code is 75080. If it is 75080, then it will emit that record, otherwise it will discard, right. So, once you process this, what will happen? You can assume that new partitions will be created, right, from B1, but that partition size will be, worst case it will be as big as this, right. If all the records satisfy the 75080 zip code, then all of the records will survive, but probably only few records will survive, right. So, this from here we will create a partition, F1 partition, F2 partition and F3 partition. F3 partition will derive from here, F2 partition will be derived from here, F1 partition will be derived from B1, and these partitions will be smaller in size, and we can easily feed this partition in the each machine's main memory. Now, I am saying, let us say on a sudden, now this B1 was running M1 machines, B2 was partition was M2 machine, B3 was M3 machine. Now, once you create F1 partition, F2, F3 partition, those will be stored where? M1's machine main memory, M2 machines main memory, M3 machines main memory, right. And if all on a sudden M1 machines is failing, then what will happen? So, then we know that we need to create this partition somewhere, and from this lineage we keep track of the lineage graph. So, we know that F1 partition was derived from B1 B1 partition, and this B1 partition is what? Is a HDFS file, is HDFS file block, right. And we also know that replication factor is 3. That means B1 block is stored not only M1 machines, it also we have another 2 copies in the clusters in some other machines. Probably it is stored in machines M5 and M7. So, in that case, what will happen? We will, at machines M5, we will read the B1 content and create a F1 block. So, that way we will take care of the fault tolerance. So, for that we maintain a lineage graph. So, lineage graph here will tell you that these are the filter partitions or filter RDD will be created. They call it, so these 3 partitions will be altogether will be known as a filtered RDD. So, recall that what is RDD? I said RDD is consists of a number of partitions or block, and each block will have a number of records, and once you create, you cannot change it. That's the key point, immutable. So every time you from this part is called actually Hadoop RDD, and from there we create a filtered RDD. Now in the lineage graph, we don't in the database world, every time you make some changes in the record, what will happen in the recovery system? They usually make those changes in the log file on the disk first, then they will update on the disk, right? That will help you to do the redo undo operation in case of failure. But here we are saying we are not talking about the details update. We are just talking about in the lineage graph that this filter RDD, we have 3 partitions or 3 F1, F2, F3 that will be derived from B1, B2, B3 Hadoop RDD, something like this. That, and then we apply filter operation for each block. That type of lineage information we will keep track.
But the RDD for B1 will now be on M5, correct?
Yes. I mean, terminology wise, is a RDD partition. In this case, this will be a Hadoop RDD, and this Hadoop RDD has, you can think about 3 partitions, B1, B2, B3. Previously B1 runs at machine M1, now B1 will run at the machines M5. And then here we have a Hadoop filter RDD that has also 3 partition, F1, F2, and this F1 is derived from B1. That type of lineage information we will keep track. Okay, so and another thing people do, if you once you create this RDD, filter RDD, there is a possibility that this, in this case, this block may be very small, so we can easily fit into the main memory. For that, you can explicitly use the cache. Cache means you will tell the system to cache into the main memory, or if you don't say anything, it will go to the disk usually. And then, but there is also a possibility that disk partition, when you apply some certain operations, and that operations may create output, that output is too big to fit into the single machine's main memory. If that's the case, then what you will do? Then it will go spill on the disk also. Okay, so we usually in Spark we write a driver, we write a program, and the driver program will start to initiate the Spark context, and the Spark context will determine various tasks we need to run at various machines in parallel, and then executor will keep track of those tasks, and some of the results we can cache it to facilitate faster retrieval. Cache it means you will put it in the main memory. So I don't know whether you can read it. So RDD is a immutable data structure, and you can cache it into the main memory by saying cache it in explicitly, and it is fault tolerant through the lineage graph. I will explain that in a minute, more details. And it is a parallel data structure, and in case of join, you can do the control partitioning. That way you can implement the what is it called? You know, in database, the join can be implemented many ways, right? Nested loop join. What are the join? Hash based join, right? Sort, merge, hash based join. So that type of thing we can do here. Okay, here the lineage graph I just want to bring your attention. So this code is written in probably in Scala. So here we take the text file and apply the filter operations, and filter we are saying if the string contains error, then keep those records, and then we will split it, and the splitting criteria is the tab, and we will take the second one, second field, and then cache it. So here this text file is stored into the Hadoop, let's say, and then we have filter operations. So, we will call filter RDD, we do the map operation, map RDD will be created, and cache operation, it will create a cache RDD. So, now what will, so I am saying this lineage graph will help us to during the failure we can do a better recovery. So, it gives you the fault tolerance mechanism, that is this lineage graph, and this lineage graph is very lightweight, because let us say I have a Hadoop file, that file has a 4 partitions. So, that 4 partition means each partition may have many copies in the system based on whatever the replication factor you have. So, now I am doing filter operation, right. So, once I apply the filter operations, it will produce small number of records from this partition will satisfy that. So, that will be, that way we will create the filter RDD. So, the basically here we have 4 blocks. So, 4 filter RDD partitions will be created, and then there we apply the map operation, it may create map RDD. Now, let us say this one is run at machine 1, this one is we are running this block, map operation is carried out, I am sorry, filter operation carried out on this block at machine 1, filter operation is carried out on this block at machine 2, machine 3, machine 4, right. So, 4 machines we are running in parallel the filter operations. Then that way we create this filter partitions, that we call it filter RDD, and then we do the map operations on top of it. So, now you can see, so this type of operations we can do in a streaming manner, or what we call it in pipeline manner, right. So, even once this filter RDD is, this partition is created for the filter RDD, we do not need to wait for the other machines to finish the rest of the to complete the filter RDD partitions. So, this it is possible that here the filter RDD has been created after 1 second, and this machine is still creating the filter RDD partitions even after 1 second. So, in that case we can continue the map RDD after that, right. So, what I am saying, this machine 1, machine 2, machine 3, machine 4, all this machine will be run in isolation or in parallel without any, they will not interfere each other, right. So, my point is M2, M3, M4, these are the 4 machines. So, we will read if this once this one is created, then we can do the map RDD immediately. This partition will be created immediately. We do not need to wait that let us complete this filter RDD for all the partitions, then we can go to the next stage. Is not that is the case. This pipelining is going on. There is no dependency here. This will be derived from exactly from this. It does not depend, this output does not depend on this or this, right. So, that type of thing we can do here. So, now I try to tell you that now let us say all on a sudden this machine M1 is not available, M1 is failing. If M1 after F1 partition is created for filter RDD, M1 machine is failing, then what we will do? But other machines M2, M3, M4 are in progress, and we know that this filter this partition for filter RDD F1 is created at M1 machine's main memory. So, what we will do? And we also know that from this lineage graph, what we know? From this lineage graph, we know that this partition was derived from Hadoop RDD, and this Hadoop RDD is nothing but a represents block B1, and block B1 we have a copy not only in the machine M1, M5 and M7. So, at that point this F1 partition now will be created running it at the machines M5 on block B1. So, that way we will take care of the make sure that the system is fault tolerant. And then why the consistency is easy here? Yes, so it's immutable, that is why we are not, it does not allow any change. And it is inexpensive in terms of fault tolerance, because lineage graph will just keep track of the partition level information, right? It doesn't keep track of all the details information and so on. And then the other point are very similar to Hadoop MapReduce. And Spark, good thing about Spark, one of the problem with the Hadoop MapReduce, it is good for batch processing. If you have a large data set, it can divide the data into a number of blocks and process it and so on. But when the data are continuously coming as a stream manner, then Hadoop MapReduce is not good for that type of processing. And so on the other hand, Spark is good for, is a framework that will help you to do, it can process not only the batch data, it can process the streaming data as well. And it can even handle the graph data and so on. So that's the beauty of the Spark. So that's why Spark is very popular now. And here I will show you some machine learning library it supports. It supports data frames, which is very similar to system or data frame. And then machine learning pipelines, it supports a machine learning library mlib, I will tell you in a minute. And it supports the GraphX to handle the graph data. And it supports not only the offline data or the batch data, it can support the streaming data. Then it gives you the high level abstraction. You don't need to write the code at a very low level. You can use the SQL type of syntax to write the queries. So that's another advantage of using Spark. And underneath the data source, it can interact with HDFS, Spark SQL, and so on. I'm sorry, HDFS and then Hive, HBase. So for mlib library, it gives you, this library is evolving actually. I should not say that. The problem with this type of product, they change frequently. So one version to another version, there is a lot of improvement. It's not a criticism, but I just say. So here they support classification, clustering, and new algorithms are added there. They support collaborative filtering. That's based on the recommendation system. And they also do some sort of features reduction technique they can support. So in your homework, you will use the mlib library to do the classification and so on. So we'll talk about that and the clustering also. So today you will learn how to use mlib library and use it for classification purpose. Okay, now that's the first part of the Spark. Now I will do a little bit programming about Spark. I will give you some introduction about how to write code in Spark. So here these two slides I just try to motivate you why Spark streaming as an important area. Many important applications will produce stream data like social network, trend analysis. You know that in the Twitter, you can, what is the current trend, like top 10 trend or top 10 keywords, you can see it, right, in the Twitter. If you go to the Twitter, this is the trending topics. So for that they use, although when the Twitter was developed, they use something else. They don't use Spark streaming. They call it a Strom framework, which does the stream processing also. In case of the stream framework, the Spark and the Strom are competing each other. And then stock market analysis, intrusion detection, where you have a real-time response or anomaly detection. There you need to deal with the streaming data. The main requirement for the streaming data, when you want to do some analytics, you need to make sure that the response will be carried out in a few seconds, even in milliseconds. So basically you need to provide real-time response. So that's the requirements here. So in your homework 4, where we talk about online anomaly detection, there we will learn how to do the how we can do it in a real-time response or millisecond. So here the main idea is this. So we want to achieve the scalable latency, that means we want to get the response within a millisecond. And so data will come from the, let us say, the Kafka queuing system or the Flume, or even for the HDFS file, and it will be fed into the framework, and then framework process the data and produce some results, and then that result will be pushed into the some storage. So here in this workshop today, I will talk about Kafka more details, because Kafka is very popular and it has been widely used for message queuing system by LinkedIn. So I will talk about that a little bit more details. So now I want to focus on the Spark streaming. So just in a nutshell, you can think about the idea here is, philosophy is for the Spark streaming. Within Spark streaming, we want to develop within the Spark framework, and Spark framework uses what? RDD, right? Resilient distributed data set. Basically, what is RDD? I try to tell you that RDD consists of a number of partition, and each partition will contains a number of records that can be derived from other RDDs and so on. So now here, when the input data are coming, the idea here in the Spark streaming framework, it will create a small batches, and the batch size you can think about 0.1. You can create what will be your batch size, basically interval size. Basically, you will create a chunk, and the chunk size of the chunk will be determined the timeline. You can say it can be, the chunk size is 1 second or half second or 1 millisecond, and then within the chunk basically you will capture a number of data points, and from this data point you will create a RDD. And then, so that's I try to say that we chop up the live stream into batches of x second. So this is x second, first x second, this is let's say this is the first x second, this is the second x second, this is the third x second. And within each x second you will have a number of records or the data points. So from there you will create, what you will create? You will create RDD. So each of this batch will create an RDD. And but this RDD, what is the advantage of doing this type of RDD? This RDD will be very small and it can feed into the main memory. For a Spark streaming case, each of this batch, small micro batch they call it, each of this micro batch will create a RDD, and this RDD will be stored in the machine's main memory. This is the key point, keep in mind. Yeah?
With the micro batch process, the second batch isn't processed until the first batch is completed, correct?
Yeah, once the first batch is processed entirely, then it will start to process the second batch. No, it's not a parallel, we cannot do it one after another. And anyway, that input, you can just think about here so you may ask me why we are not considering first, instead of the time wise, they divide the batch by time, right? So first x second will form batch 1, second x second will form the second batch, third x second will form the third batch, something like this. Why don't you do it, say first 1000 instance will form batch 1, second 1000 instance will form batch 2. That's another option, we can do it. But what is the problem with that? The problem is there is a possibility that the input data stream may not produce the data at the same speed, right? So it may produce some data and it may not produce the next any data points. So in that case, you have to wait a very long time. So that's why we choose the time unit as to determine the batch size. Okay, so that's the thing so far I covered. And okay, what time is our break? Okay, so next lesson you will learn. Oh, okay, we'll do some programming. So there are some slides talk us about how to set up the Hadoop Spark clusters and so on, but that may not be relevant in this setting because we already installed the Spark clusters and single node Spark clusters. But if you, in future, if you want to do it from your facility, you can use this Spark setup slide. Now I'm saying we provide some slide how to set up the Spark cluster, but that may not be relevant in our setting because we already installed the Spark here.
Question.
Yeah.
You're using it for streaming. How does Spark compare to Storm?
Actually, yeah, that's a very good question. 2 years back, we did an experiment. We captures VMware memory uses, CPU uses, performance data, and send it as a streaming manner. And then we process it using Spark and Apache Spark and the Storm. There, we observed that Spark was doing better. But now I saw that there is a new write-up from Storm. They're claiming that they improve it further. They're claiming that they're doing well. So, but there is a race going on between these two companies. And there is another company from Germany, what is called Flink. So they also do well in Sparks, I mean in the streaming area. So in 1 month, one company is claiming that they're doing well, which might be true, but then after 2-3 months, you will see the new version will be released from another company that doing extremely well. But yeah, but both performance are reasonable, you can say. Okay, so I just want to give you an idea how we can write the code in Spark. So here I said RDD, so I want to talk about more details how we can create the RDD. And here we will use, first we will tell you simple RDD, then we will talk about the pair RDD, means key value pair. So here you can launch a Spark shell. So here we want to create a RDD. So in Python, this ABC is my 3 data points I have. This is a very toy example. And that will create a RDD, sc.parallelize. That way you can initiate your RDD. And then text file can be loaded. If you, any RDD you want to create, you need to make sure that you use Spark context. SC means Spark context. So that way you will initiate the RDD. So this code is written in Python. Okay, now, in Spark, there are 2 types of operations. One is called transformation, other one is called action. Transformation means you may have the original RDD and you create a new RDD from there. And transformation usually is a lazy operation. That means that when you write transformation operations, the compiler will just do the syntactic check and that's it. It will not produce any result. But when the compiler encounters first action operations, then it will produce, it will materialize all of this. Basically, it will execute all the transformation operations all the way to the first action operation. And here we listed some transformation operations. So here, first transformation operations, I just give a name called map function. So let's say in a Scala, we say we have a list which has a 1, 2, 3 numbers. Now, number 1 has 3 elements in the list, and number 2 has 3 elements also. Now, I want to do a map operations, and in this case, the map operation is something like this. I'll take each element, what we are doing here. I know a little bit Scala better than Python, so that's why I prefer Scala over Python. So, here we will take each of this element, but this code is written in Python. So, we will take each of this element and then square it, right. So, that way you can write the code in Scala or Python for map operation like this. Scala code is very compact, and then this one we take the nums. What is nums here? I think there is one problem. The problem is no, it's fine. The reason I'm saying, okay, so num1, num2 should be nums. Sharp, can you correct that? So num1, num2 should be nums, right? Or nums. Anyway, so the point I'm trying to make here. Okay, so let's say this part of the code is so okay, we have a nums is 1, 2, 3 elements, and when we apply the map operations, it will produce, it will take first element, produce 1, 4, 9, something like this it will produce. And then for filters, we are taking the nums and we are doing filter operations what? If it is even, then the element will survive, right. So, it will produce from okay, I'm sorry, I made a mistake, I did not check.
You have in the Python the square set filter, but you don't have it in the
Python is correct, right? Yeah. So, this one needs to be correct in Scala. So, they will correct it, yeah, you are correct. So, in Python we are taking squares. So, squares will be 1, 4, 9, and when we apply the filter it will produce. So, 1, 4, 9, only 4 will survive, that is correct. And then we have a okay, the important point I am trying to make here, map and flat map. What is the difference? Map, it will take each element, produce a new element and produce a new list. But flat map, it will take each element and it may produce more 0 to more elements. So, the difference between map and flat map, both apply the function, right. So, you will take the map case, it will take each element and apply the function, and after applying the function it will produce a new element. So, eventually it will produce a new list. But in flat map, it will take a element as an input, apply the function, and this function may produce 0 to many elements. So, that is the difference. 0 or more output means from one element 1 to 1 mapping here in case of map, but here flat map case 1 to many. Is it clear? So, here is an example. If I say even dot flat map, and what is even? Even is 4, right, and flat map I said range 1 comma x comma 1. That means you know the range function, what does it do? If I say range x, it will start, if it starts from 1 to x 1 to all the way x minus 1. So, in that case it will produce 1, 2, 3. For 4 it will produce 1, 2, 3. Is it clear? Then we can do the union. So, if I take two numbers, number 1, number 2, if you combine it, it will produce, union will produce something like this. And if you take the intersection, it will produce intersection between this two, it will produce 2, right. Then distinct, it will produce the distinct elements. Num2, what is the distinct element? Only 2 and 5. Then these are, so far I covered the transformation operations. Now I want to talk about action operation. Like action is a collect is the action operation, retrieve the RDD contents as a local collection. First k elements, num take, you can num count how many elements are there. Then you can reduce operation, reduce is a action operations. You can say I want to reduce. So in that case it will produce, here what you are saying, nums dot reduce and x plus y. So we will take will sum each element and produce the result. So 1 plus 2 plus 3 is 6. So the key point here, you will hear this one very frequently. We want to use the key value pairs. So for key value pairs, let's say if the pair is a comma b, and in Scala you can access the pairs like this, pair dot underscore 1, pair dot underscore 2. In Python you can do like this. This is very important syntax, try to memorize it. And then now we want to talk about some group by operations. So then I will tell you famous example word count, how we can do it in Hadoop MapReduce, how we can do it in Spark. Okay, so here let's say we have a the data has a key value pairs. So first key is the word, apple appears 2 times, orange appears 5 times, apple appears 1 time, orange appears 2 times, and this number 3 means how many parallel processing you will exploit, or the so this will help you to do the parallel processing. That, and then here we are doing the group by of key. So group by key means what will happen? Group by key, data group by key, it will produce apple, and based on this, these are the values we will get. So apple has a 2 times it appears, the value will be the 2 comma count and the 1. Then reduce by key. So here we are saying reduce by key. So I think that's an error also. It should be reduce. Sharp. So it should be reduced by key. And then in this case, this one is we are saying you can write like this, reduce by key. So here we are saying, we'll take the values and sum it up given key. So that shortened explicit notation like this, but in shortened notation we say something like this. But in Python it is more straightforward. So here for apple we have how many apple? Apple comma 2 and apple comma 1. So 2 plus 1 it will produce 3. So for each word we can count how many times it appears, that type of thing we can do by using reduce by key, and sort by key it will produce something like this. So now let's talk about famous word count example. When people talk about Hadoop MapReduce, they always give you an example on the word count, right? So what is the example word count? We have a large number of documents and we want to calculate how many times a particular word appears in all this, in the entire collection of documents. So how we can do it? If I give you that, I give you millions of documents and I ask you for each distinct word, can you tell me how many times it appears in this entire collection of documents? What you will do? One naive implementation, every time you encounter a word, you will put it into the hash map, right? And then if the word is a new there, then you will just set it 1. If it already exists in the hash map, then you will increment the count by 1, right? That's the simple implementation. So that, but if I want to do it in a Hadoop MapReduce, what we do in the past, I haven't covered it, but the idea is mapper will, every time mapper encounters a word, it will emit the word as a key and the value will be count 1, right? And the reducer will get a given word and the list of values, then it will aggregate them, right? Because keep in mind that mapper emits intermediate key value pairs, and the reducer expects the intermediate key value pairs having the same key will end up with the same reducer. That's the very basic principle in Hadoop map reduce case. So now in word count, I want to do it using using Scala. I'm sorry, using Spark. So for Spark, what I will do, I will take the file lines, and then now I need to take each line and tokenize it, right? So what should I use? Lines.flatmap, and in that case these are the dummy variable anyway. So line implies line split. So that way I will generate the token. Now each line will create, each element will create many elements, right? So that's why I need to use flat map. If you try map, it will not work. Is it clear? Because you are taking each line or each row and tokenize it, and those token will be splitted. And then for tokenization, I am using the split function that tells you that the separator is the blank space, then it will create a new token. That way many tokens will be created from a single line. And then now I need to generate a pair, key value pair. In this case, the key will be the word and the value will be count 1. So there I say map word, each token implies word comma count 1. And then I am saying reduce by key. So every word I will aggregate their count. So that way the code is written. So this code might be a little bit difficult to understand, but if you know the Hadoop map reduce word count, then it will be trivial too. So do you have any question? No? Or you are lost? I hope it is over. If you have a question, please ask me. Okay, here is a diagram that tells you. So these are the lines, let's say, in the hamlet.txt file I have. The first line is this, and then lines flat map will take this and split it. Line split will create 2B or like this. And then, so from 2B or after flat map, once you apply the flat map, it will produce something like this. So from each line, it will create more than one elements, right? Think about this as a single element. From that element, we are creating 3 elements. So that's why I am using flat map. And then I am applying the map operations that will produce key value pair 2, 1, B, 1, or, 1, something like this. And then reduce by key. So for a given key 2, I have 2 here. So it will produce 2, 2, something like this. Then we can do a join operations in Hadoop in Spark. So here we have visits table and the page name table. Visits table has a column called URL, let's say dummy example, and the second column is called IP address, let's say dummy example, and then page name has a URL or the joining attribute, and the second column is the type of the page, say home, about, or something. Now if in a Spark, when you do the join, you will say first table dot join and the second table. So it will produce the joining attribute, and the remaining attributes will come here like this. And if you can also use the co-grouping. So you know that in database, when you do the join in database world, if I want to join R relation with S relation, if I have a tuples in R and that do not join with any tuple of S, then if you do a natural join, then the tuples that appear in R doesn't have a counterpart in a tuple in S, that will not appear in the result, right? So what do you do if you want to keep it? You can do a left outer join or some outer join, right? So similar concept here, co-grouping. If some tuples exist in one relation and or in one table, another table doesn't exist any values, so then in that case still it will survive there in the co-grouping case. But here is the toy example. So in the co-grouping case, this is the joining attribute, and this will come from the first table's visits remaining attributes, and then this is the second table's remaining attributes. And there is a possibility that some attribute may be null in this case. And that is the difference from co-grouping with respect to the join. Okay, so this extra parameter, I try to tell you how many tasks you want to run, that you can specify here. So I have a little bit more examples. So here is an example. We try to say, what we try to say? Okay, so here is the requirement. Say we consider the code that starts with odd lines of text and the first word of line as the keys. So here we can say we want to map the line with take the first one as a key, and the whole line will be as a value in this code. And then here is a sample key value pairs we have. This is the key and this is the value. And now I want to apply map values operations. So in this case, data dot map values, recall that data has this apple, orange, apple, and so on. So if I say, okay, so what is the this transformation operation on pair RDD? Map values is the important features. What does it do? It doesn't map values work on the value part. It doesn't change the key. So if I need to make some changes in the value part, so I will use map values. Say for example, I want to increase those value part by 1 for each of these values. So I will say data dot map values x implies x plus 1. So apple comma 3, orange comma 6. So it will produce something like this. And then and then we have a keys values, so that way you can extract some other properties. And then here we try to say how we can use the case operations. Say for example, I want to do a filter out lines larger than 20 characters. So basically I want to keep the lines which is less than 20 characters. So I will say pairs dot filter case key value implies value dot length less than 20. Then I want to show you one important point. Let's say, okay, so that part we already covered. So now we can do the reduce by key. That is similar to the actions on the RDD that we already covered. And then okay, so now let's say this is the example I want to go through. So the key value is this x, y, z. These are the keys, and the value is this. And our goal is to, for a given key, I want to calculate the average. For a given key, I want to calculate the average. So here I am saying x appears 1 times, x appears in this case 5 times. So for this x, I want to calculate the average. What will be the average? Key is x, and we have two numbers, 1 plus 1 comma 5. So it will produce 1 plus 5 divided by 2, right? 3. So if I want to do it, how I can do it? So in order to, for a given key, if I want to calculate the sum and the count, and then from there I can calculate the average, right? So for that, what I will do, I need, in order to calculate for a given key, in order to calculate given key, I have the values. So from there I want to, given a key, I want to calculate the average from the value. So in order to do that, I need to know the sum and the count. If I know the sum and count, then I can easily calculate the average. Sum divided by count will be the average. But in order to do that, I need to convert these values into a pair. So in this case 1 comma 1, 0 comma 1, like x 5 comma 1. So, that way every numbers I will have a count 1, and then for a given key I can reduce their sum, basically aggregate their sum for a given key and aggregate their count. So, in that case for x I will have 6 comma 2, and then from there after that I can easily calculate the average. So, if I want to do that, here the code I will use. So, let us say RDD holds this. So, at the beginning RDD contains this type of structure, points to this. Now, what I will do? I will say RDD dot, what value I need to change? I need to convert this value to a pair. So, I will do something like this. I will say map values, because the key will not be changed. Map values only change the value for a given key. So, now the value will be changed to a pair. X will be x comma 1 dot reduced by key, and in that case what we are doing reduced by key. So, now keep in mind that after map values what we have? We have this, we have the value, but value has a two pairs, right? Value has a pair, not two pairs, value has a pair. Value has two entries, the first entry and second entry. In a Scala, first entry you can point out dot underscore 1, second entry you can point out or access it dot underscore 2. So, that we are doing exactly here. So, here we are saying x comma y, now x and y for a given key, x will have a pair and y will have a pair, right. X has a sum and the count, and y has a sum and the count. So, what we are doing x dot underscore 1, that means we are doing the sum here, producing the, for a given key we are producing the sum, and we are here in this part what we are producing? Local count, we are producing count, and then after that you can write how we can calculate the average. I haven't shown you, can you give me an idea? Huh? So, what should I use after that? So, you have this and then dot, what should I put? Very good. So, yeah, that is why you guys work in NSA. Now, if I ask this question to my class, they may not answer it, but so yeah, you have to use map values, then
Function is x, fancy arrow to x dot underbar 1 divided by y dot.
right. So, one option is probably I will use case sum comma count implies sum divided by count.
Depending on whether you want an integer condition or not.
Right, yeah. So, something like this. So, let me see whether I wrote correctly or not. Okay, I took your time. So, let us have a break for half an hour and then we will start again from here. Okay, so I don't know whether you can see it, but I wrote a okay, so from here I want to calculate the average that I said. So, you don't need to use dot map values, and then this numbers will be divided by this, that way you will do it. So, there is another way you can write the same code, RDD dot map values and then reduce by key, then case sum L comma count L comma sum comma R count R. Basically, you will do the left part, you will first part you will do the summation, and the second part you will do the count, and then you will do the map values and using the case. Only the important part is for when you use the case, you have to use this bracket. And then there are some action operations on the pair of RDDs. So, if I have RDD like this, count by key, it will produce something like this. So, you can extract the key. Collect as map, it will produce the you can get the as a map, you can retrieve it, and then lookup key. So, the value you can retrieve. And more details you can find here. So, I just give you an idea how the things works. Now, do you have any questions so far? No?